Hello, my name is Tomoyuki Saito from the Line's Data Platform Department. I am currently leading the R&D and development project as the Senior Software Engineer at the Data Platform Development Organization. In this session, I will introduce some of the challenges we faced in developing and operating the data platform and the efforts to solve them. This session is divided into two parts. In the first half, I will talk about the data processing, and in the second half, I will talk about the challenges of data ingestion pipeline and the efforts to solve them. First is the introduction to Line's data platform. Line has a data platform that aggregates all the data from the various services provided by Line and offers a comprehensive data analytics environment. The data platform provides a self-service function to address the data analytics and machine learning requirements or data governance requirements and support democratization of data. The data usage flow of the data platform can be categorized into three major processes. The ingestion process to aggregate the data onto the platform. The process to process the data so that it meets the data analytics requirements. And the process to provide the data in a way that it is easy to use for decision-making or service development. The characteristics of Line's data platform is that the volume, types, and the scale of usage is large. With the growth of users and service, the data scale becomes greater, and the platforms and infrastructure that addresses the analytical requirement also needs to scale out. Let me introduce you the scale of data currently handled by the data platform. Number of machines used in the platform exceeds 5,000. The volume of data exceeds 290 petabytes. The number of Hive tables exceed 40,000. Number of logs ingested in the log ingestion pipeline is 17.7 million records per second. Number of jobs executed per day is 150,000, and the number of users on the platform exceeds 700. The data platform, while the data scale is expanding, provides services to execute the processes needed for data analytics. We need to build a system that scales even with the high throughput for the data ingestion platform, even with the large types and volume of data for data processing platform. Now I will talk about the challenges we face with the services that support Line's data processing. First, I will introduce the outline of query execution for data processing. The data processing for analytics is typically done by SQL. In executing SQL, the SQL query engine enables distributed processing of data. This diagram shows the process done by the distributed SQL query engine. The SQL query is transformed into execution plan for each distributed process engine, and ultimately this is executed using the compute resources allocated by the resource management system. In order to transform the SQL query into an execution plan, it needs information such as where the data is and how the data is read and written for the tables specified by SQL. The way to manage the information of the table needed by the query is defined by table format. Table format defines the file's management method so that a particular dataset can be expressed as one table. Table format serves two main roles in query execution. First is to tell which file comprised the table's data, and second is how the file can be read and written. In order to do this, it requires metadata management, such as partitioning and schema definition. The de facto standard for table format is the Hive table format. Hive table format manages the data file using the directory of the file system. Modification and referencing of metadata, such as partitioning and schema used for management of tables, are done through a server called Hive Metastore. In the background of Hive Metastore, metadata is stored in RDBMS. Here we call this backend DB as Metastore DB. With the Line platform, it is typical to manage the tables using this Hive table format. This is how the system provided by Line's data platform looks like this. HDFS used to store data, and Hive Metastore used to store table metadata are written on the storage layer. The SQL query engine provides the environment to allow execution of Spark, Hive, and Trino. The analyzer of data uses these SQL query engines and execute interactive queries or deploy ETL pipelines using Scheduler. With the expansion of data usage at Line, we have experienced various troubles related to this Metastore. The Metastore instance builds a multi-tenant environment that is shared by all the users of the platform. Therefore, the trouble of Metastore gives significant impact. This shows the query rate of the Metastore DB. These are DML execution rates, top showing select statement and the bottom showing updates. As you can see, in the data platform environment, select statement QPS is high, and about 5,000 queries are executed per second in a normal state. Next is the CPU usage. As you can see, the usage exceeds 50 to 60% during busy hours. This is an example when abnormal CPU usage was observed. You can see that the CPU usage is close to 90% at one point. When we searched the cause of this trouble, we found that the Hive table with more than 10 million partitions were involved in this issue. In the case of this trouble, we were able to solve the problem by deleting the partitions that were unintentionally created. Hive table format is designed to manage metadata using Hive Metastore. And for partitions, it is designed so that one partition is stored as one row in Metastore DB. In the operation, we identified that troubles tends to happen when large number of partitions are used like we saw with this trouble. Sometimes a heavy scan is executed on the Metastore DB, causing the response to slow down, or we've experienced troubles with the Hive Metastore server having large number of partition objects being loaded onto memory, causing the memory pressure becoming high, making the system to go down due to full GC or OOM. Due to this limitation, we need workarounds such as reducing the number of partitions or limiting the number of partitions being handled at one time. In summary, these are the issues we face with the Hive table format with Line's data platform. With the Hive table format, the DB capacity of Hive Metastore and Metastore DB became the bottleneck, causing the performance of referencing table metadata to be limited. Hive Metastore cannot handle large amount of partitions, so the table needs to be partitioned using coarse-grained partitions, making the data access to be inefficient. Due to the Metastore capacity, it is unrealistic to change the model, such as adding metadata such as per-file statistic information to optimize queries. Up to this point, I have explained what Hive table format is and its issues. At Line, we are focusing on a table format called Apache Iceberg to solve the issues we faced with Hive table format. I would now like to talk about what Apache Iceberg is and what benefit it brings. Apache Iceberg is an open-source table format. As with the Hive table format, it abstracts the file format or the file layout on top of the storage against the SQL query engine. This is how it looks when Iceberg table is used. By using the library for Spark that is provided by Iceberg, the Iceberg tables can be handled by Spark SQL. By describing the create statement, the Iceberg table format can be specified. Here onwards, the SQL statements, such as select or insert, can be executed like with any ordinary tables. Bottom shows the file layout on HDFS. The table we created is called sample, and under sample directory, directories called data and metadata are created. I would like to show you the details of this metadata file. There is a key concept called snapshot with Iceberg. Table format is a way to abstract what data comprises the table in SQL query execution. Iceberg tracks the file by managing the status of the table's file as snapshot. The snapshot means the same as the general term, and it is the state of a table at a certain time. In the example in the diagram, the state of the table at point T0 is saved as S0, and S0 has the reference to the file that comprised the table. The role of table format is to track and manage the state of the table, even if the table is updated. Iceberg creates a new snapshot like this when data is written and committed. In the example in the diagram, a new file is added, and the S1 snapshot stored reference to all the files including the data as of T0. In order to access the data as tables, it stores data's schema and data's statistic information in addition to the file path as metadata. Let me show you the specification of Iceberg in a little more detail. The metadata directory I showed you earlier is an aggregation of files like these. Table metadata file is the file showing the current state of the table, and it stores the snapshot information that I explained earlier. Snapshot has the reference to the manifest list file and stores the list of manifest files. Manifest file is directory storing the metadata, such as data file paths and statistic information. Iceberg uses such hierarchical file structure to efficiently track and manage data and metadata. The biggest difference of Iceberg table format to Hive table format is that the state of the tables is tracked using files. This can eliminate the dependence on Hive Metastore, which was the bottleneck with the Hive table format, and allows us to use scalable file systems such as HDFS as place to store metadata. Let's look at an example of query being executed on data. Because the state of the table is managed using snapshot, the current snapshot is referenced and accesses the manifest list file that is specified. The manifest list file stores the upper limit and the lower limit of the partition value of the data managed by this manifest file. If there is a partition filter on the query, the manifest file that is actually read can be filtered using this range. By reading the manifest file that matches the query, we can obtain the path to the data file. This is how the file is tracked by Iceberg, and it also supports data partitioning. As a benefit of storing metadata into file, the capacity of storing metadata has increased. The manifest file of Iceberg stores per file per column statistics information, and this allows to further reduce the number of files actually being read during a query. This is the summary of the differences between Hive table format and Iceberg table format. With the Hive table format, the metadata was stored in Hive Metastore, but with Iceberg, it is managed as file. With this, the bottleneck of a Hive Metastore in metadata management was solved, and the scalability was improved. The number of partitions were limited due to the capacity of Hive Metastore, but this was solved with Iceberg, enabling a more efficient table structure. The statistic information was limited to partition level in Hive, but with Iceberg, it can be managed per file. With this, we can expect improvement of query performance. Iceberg has many other designs to fulfill analytical requirements, and we think we can effectively utilize them to address other data platform issues. This is a summary of today's presentation. The Hive table format, which is the current de facto standard, had the scalability issues due to Hive's Metastore being the bottleneck. Apache Iceberg uses files to track data and solve this bottleneck. Also, the design of Iceberg is expected to help solving the other issues related to analytics. With this background, we are considering to widely adopt and utilize Iceberg table format with Line Data Platform. This is all for the first half of the presentation. Thank you very much for your attention. Now I will move on to the second half of the presentation.
Now I am a speaker from here. My name is Takeshi Ono. I belong to Data Engineering 1 team, and I started to work at Line in 2019. I'm working on the development of ingestion pipeline. This is the agenda for the second half. I will cover the overview of the existing log pipeline, problems of the existing log pipeline, and how these problems will be solved by introducing Iceberg, Flink Iceberg application details, and finally, how we proceed the project in the future. So this is the overview of the existing log pipeline. This slide shows the first level of the existing log pipeline. Originally, it was a simple architecture. Kafka, Flink, HDFS, Hive table is append only. users define the schema with the protocol buffer and the protocol buffer or JSON message to Kafka. Flink will consume that, and without converging the record, it will add that as sequence file format. We call as raw table because it retains the data from the user as it is. User can read it by using a special CERD. By utilizing checkpoint mechanism of Flink, it is supporting the exact once delivery. Deserialization of the protocol buffer is high speed, but the number of users and the table have been increasing, so young computation resources are starting to deplete. That is because we have to deserialize the sequence file 1 in 2 lines, so we decided to introduce column format. We introduced the ORC table as faster column format. Watcher is frequently checking the update of HDFS file per partition. When update is detected, insert override query is executed through Hive server 2 and it converts raw data to ORC. Since this is an ORC file, so user can read the table without any special CERD, and all tables are external tables. So we keep original raw table pipeline as it is, and the conversion to ORC table is added. It is 2 steps architecture. Next talk is about problems of the existing pipeline. The first problem is it takes a long time to end. It takes 1 to 2 hours from log generation to it can be read as table. There are some reasons for that. When there are many small files, the memory usage of the NIM node increases, so we have a small file problem. In order to avoid that, Flink application is trying not to generate the logs by using a bucketing sync, which is supporting truncate. To the partitions that are created hourly, raw table sequence file is flashed in every hour. So at this point, 1 hour latency is happening. The ORC table conversion is done, and the number of the tables is quite large, so it takes 50 minutes to complete. So 2 hour latency is there. According to the latest data or service provision, this latency needs to be reduced. So we can have the ORC file directly output. Flink streaming file sync and ORC writer of the Flink are used. This sync can make a direct output of ORC, but it is not supporting the truncate, so at every checkpoint, some minutes, file is flashed and closed. As a result of that, end-to-end latency can be reduced to a few minutes. But implementing the compaction turned out to be difficult. After compacting small files, we need to replace the files. Our Hive is not the latest HDID Hive, so at the moment of the file replace, there will be the file loss error. And there will be logs coming in later. We have to scan a large number of directories in order to detect which file needs to be compacted. And scan cost to name node will increase. There is a risk of error and complex implementation and high cost of resources. So this proposal was not accepted. Next, we have an issue related to the system robustness. First, there are too many components. Because we added ORC conversion, all components such as Flink, Watcher, HDFS, Hive, Metastore, Hive Server 2, and Yarn should work properly, otherwise pipeline will be stopped. If there are so many dependent components, there will be high possibility of the failure, and it will be difficult to do the root cause analysis. Then we have an operational problem. Table partition is fully automated, but when user makes a specific request, we need manual operation. Each log has two types of table, and since there are external tables, so we have to process metadata and file respectively, which is likely to have the mistake. And then there is a high load issue. Since there are many tables, so a lot of information and the partition information are stored in the name node and the Hive Metastore. And when we plan the query or watch checks the partition, there will be a lot of load on these components. And finally, we have limited schema evolution support issue. For ORC field mapping, we adapted the position base. But name-based mapping is also adapted from Hive 3, but position base is still used in order to be compatible with the existing system. So it can do only to add the field to table struct. In order to delete, insert, and move, you have to recreate the previous data. Otherwise, it will be error. Rename is possible, but we have to change the client setting of the Spark, so it is not recommended. Sometimes a user wants to delete the unused field or insert the new field to the place which can be easily found. So let's take a look at how these problems can be solved by adapting Iceberg. First, an overview of new log pipeline. Basically, it is the same Flink architecture of which output ORC directly, but that was rejected. The difference is that the Flink writes the column file such as ORC park directly to the Iceberg table. And then there is a table optimizer which maintains the table. Flink flashes the file in every 5 minutes. Table Optimizer executes each Spark action which is provided by the Iceberg in order to do the maintenance of the table. Flink does the flash and the close at the checkpoint, and latency can be reduced to 5 minutes. So, from the moment of the flash, we can read the column format file. And we face a small file compaction issue, but since Iceberg has a snapshot mechanism, there will be no failure at the time of file reading. Flink is writing now, and the Spark can do the compaction safely even to the partition that is read by the user. The green line on this diagram shows the timeline, and the time proceed from left to right. Flink write in 000102 in every 5 minutes. When 03 gets created, which is a snapshot 010 timing, compaction will be started by Spark in parallel with the Flink, and it tries to merge the file from 00 to 03. Then Flink creates a snapshot 011, which includes 04, and Spark finishes compaction and then create the snapshot 012, which include 05 that was merged. Even we started the reading right before snapshot 012 gets created, there will be no loss of the file. Snapshot will not disappear unless it gets expired. So snapshot before 011 still remains after compaction. File from 00 to 04 remain. And after snapshot 012, files from 00 to 03 are not included, so it does not have the duplication problem. And architecture will be simple and scalable compared to the current one. Pipeline does not need a 5-server 2 and a yarn, so it is a simple configuration and less factors that might cause the failure. Of course, a table optimizer depends on the Spark on yarn, but it does table maintenance. And then even though the job gets delayed, it is not fatal to the services. With the hidden partition feature of the Iceberg, there is no need to do the file partition management which was needed for the Hive external table. And if you want to delete all the record, you just have to issue delete query, and you do not have to delete the partition file. And the load is reduced on the name node and Hive Metastore. As we touched upon in the first half of this session, table and the partition file information are written as file in the Iceberg. When we plan the query execution or when table optimizer checks each partition condition, there is no scan to name node and Hive Metastore. And schema change, which could not be done so far, is now possible. Addition of the field, rename, delete, insert, move, all of the changes that are done by protocol buffer scheme are now possible. As a rename, move is also supported because a unique ID is assigned to each field internally. It is not a position nor a name. Each change is traced by using that ID. Here's a summary. Small file problems, end-to-end latency, schema evolution, and scalability. All of these are solved by introducing Iceberg. Let's take a look at the details of Flink Iceberg application implementation. When we use Flink's DataStream API, we have to convert it to raw data type, which is used as an input. It is used as a record type, so protocol buffer and the JSON must be supported. And Iceberg supports many types which has keys other than timestamp and string, so we have to convert to int64 to timestamp or cast JSON's string key. And enum of the protocol buffer is not supported, so it needs to be converted to the string. In the current implementation, we converted it to Avro once because we used the conversion of the protocol buffer to Avro process. If you use a Flink Avro reader that is provided by the Iceberg, you can convert that Avro to raw data that can be used by the Iceberg. Current implementation works fine, but in order to enhance the performance and to make a more simple design, we are considering conversion directly to the raw data without converting to Avro. Flink provides the library which can convert each format to Flink's row table. JSON has a Flink format. Flink JSON and the Flink protocol buffer package for the protocol buffer is planned in Flink 1.15. By using and referring these libraries, we want to proceed the implementation of the direct conversion of the protocol buffer JSON. Here are the details of the Flink application implementation. In case of Iceberg, Flink data flow graph is consisting of a multiple stream writer and a single file committer. Consumer will import the data from Kafka, and the data will be converted to raw data by the converter and sent to the writer. Writer receives the record and will write those in the proper partition of the Iceberg table as ORC or PARC. When Flink checkpoint barrier will reach the operator, writer closes the file and sends the information such as a path to the committer. Based on the file information, committer creates a manifest file based on the file information and commit a new snapshot to the Iceberg table. This commit should happen only once, so only one committer exists in the flow. If the processor fails at any point of this checkpoint, Flink will do the process again from the last successful checkpoint, so there will be no loss of the data. If an update fails to commit, will not be reflected in the Iceberg table, so there will be no duplication. Which means delivery is done by exactly once. And Iceberg provides a Flink sync. This is an encapsulation of data flow graph, which is consisting of a writer and a committer, and it is simple to use this if there is no performance issue. But we are not using this. Each consumer consumes one Kafka partition, But when there is a large volume of data that is coming in from Kafka, it needs to increase the number of writers. In case of Flink sync, we increase the number of writer by increasing parallelism. In that case, there will be a shuffle, which is the redistribution of the stream among different parallel operators. So data will be transferred through a network among task managers. Some of these tables that are processed by the pipeline have more than 1 gigatype per second, so we want to avoid unnecessary load of a network transfer. So we are introducing the splitter in order to increase the number of writer without changing the parallelism. With this mechanism, we can change the number of the writer dynamically according to the volume of data. So there's no data transfer through network among operators. There will be no performance degradation. We can also address the rapid data volume increase. I will skip the details of the implementation. We use a Flink side output. Finally, I want to go through the future works of this project. First, we verify the stability and the scalability and the query engine of Iceberg table and start thinking the migration plan. And we will replace the Hive table, which is used by the data pipeline, with the Iceberg table, and adapt the incremental read, Iceberg unique feature such as incremental read and update per line and the time travel. We're looking for the people who can work in the following positions. Please make an access to the site if you are interested. Thank you for listening.